with me. So the summary is that intermolecular forces are between molecules, and the first one is a permanent dipole. So what's a permanent dipole? First thing is, how are molecules formed? Like, you've got an H atom, right? And you've got a Cl atom. So here's this much bigger Cl atom. Now Cl has 7 electrons in its outer shell, and H only has 1 electron, right? So the thing with these atoms is that you have this periodic table. When you move to the right of the periodic table, and when you move in the upward direction in the periodic table, when you move to the right and when you move to the top, there's a thing called electronegativity. Your electronegativity increases. The atoms, they become more and more electronegative, right? That is basically, they like to gain electrons. I mean, simple words, they have this tendency to actually gain electrons, and the reason for that is that the nucleus becomes more. I mean, when you move to the right, you have more protons. I mean, there's more positive charge in the nucleus, so which is why you're obviously going to try and gain more electron. Like, you have lithium over here, which only has 3 protons, and you've got fluorine over here on the right, which has 9 protons. So obviously fluorine's nucleus has a charge of +9, so it's more positively charged. It's got 9 protons. Lithium, on the other hand, just has 3 protons, so it has a charge of +3. So obviously, fluorine would try to gain more electrons. Is this clear?
Yes, sir. It's clear.
So there's a thing called electronegativity, which increases when you move to the right corner of the periodic table. Now, the thing is, how is a covalent molecule formed? Covalent molecule is formed because atoms, they would try to gain electrons. I mean, this nucleus in the center over here, chlorine, would see this electron in hydrogen and would try to pull it towards itself, right? So it would try to attract that electron. But the problem would be that H is also very strongly attracting that electron. H is not letting it go. So what would eventually happen is that shearing would start. What that means is, imagine the Cl trying to pull the electron, but the H is not letting it go. So what would happen is that the entire H atom would get dragged along, and Cl would pull the entire atom along with the electron. Is this idea clear?
Yes, sir. It's clear.
So that's what a covalent bond is. So in any covalent bond, you've got 2 atoms which are basically trying to fight over electrons. So you've got, in this case, you've got H and Cl. No one is letting go of those electrons, so no one is losing or gaining electrons. Cl is trying to pull the electron in this direction. H is also trying to pull the electron and keep it with itself. The end result is that the electrons, they get stuck in the middle. So they are exactly in the middle. So is this point clear?
Yes, sir.
Now the thing is that these electrons, they don't usually. It's like a tug of war. One of the atoms is trying to pull the electron to one side. The other atom is trying to pull the same electrons to the other side. Now, the electrons would be exactly in the middle only if the 2 atoms are pulling the electrons with equal force. You can think of two guys, uh, and they're pulling there's a tug of war happening, and they have equal strength. So the rope would remain exactly in the middle. Is this idea clear?
Yes, sir.
But the thing is, the 2 atoms are not pulling the electrons with equal strength. Cl is slightly stronger when it comes to attracting these electrons. So these electrons are going to be kind of, they're going to be closer to. Just a second.
Cl.
Okay, so they're going to be slightly closer to Cl. Just a second. Let me just. So the electrons would be slightly closer to Cl. And the difference is not that much. It's just that they are slightly closer. In ionic, what happens is that the electrons get completely gained by Cl. So when the electronegativity difference is huge, that's ionic. The electrons would be completely, I mean, H would completely lose those electrons and Cl would completely gain those electrons. But no, but not in this case. The electrons are just slightly closer to Cl. So which is why Cl is going to have a very slight or partial negative charge, and H would have a very slight partial positive charge. Is this point clear?
Yes, sir.
So when you see next time when you see and there's I mean we can have a look at the Pauling scale, which is not in your exam course. But I'll just give you an idea. That'll just give you an idea that second. Okay, so both of them are no, they're both tiny. Okay, that's. I mean, we can't read. No, we can't read the number. Just one second. Why are they so small? Okay, leave it. So this is a Pauling scale. It just shows electronegativity. So for example, over here, I mean, you can't really see the values, but Cl over here is probably 3.16 and this is 2.2, so it's clearly more electronegative. Uh, so I mean if it becomes darker, that's more electronegative. So Cl and H are kind of, Cl is slightly more electronegative. So what happens is that the electrons are closer to Cl, and the end result would be that it's going to be a pole. This is called a permanent dipole, right? Is this clear?
Yes, sir.
So that's your permanent dipole. Now the thing with permanent dipoles is that when you have an HCl molecule and when you have a bunch of HCl molecules, these permanent dipoles are going to create an intermolecular force of attraction because Cl is partial negative, H is partial positive. So the partial negative H and Cl, they would attract each other. Cl is partial negative, H is partial positive. So they are going to be, H is positive. So there's going to be a mutual attraction, which depends on the size of the dipole. So if there's more difference in electronegativity, there's going to be a stronger dipole. So is this point clear?
Yes, sir.
So the thing with dipoles is that the two things. One is that there has to be electronegativity difference between atoms in a bond. The other one is that the other one is the dipoles should not cancel out, and for that it's shape that matters. I mean you have to be or you have to have an idea of what the shape of the molecule is. So the shape matters. So the thing is, like if you have a CO2 molecule, the shape of a CO2 molecule is linear. The angles are 180 degrees. Now, what happens over here is that oxygen is more electronegative, so oxygen would be pulling electrons towards itself, right? Slightly more. But both oxygens are pulling the electrons at different ends. So, where would the electrons end up? They're going to remain exactly equally shared. They're not going to go anywhere. So, is this point clear?
Yes, sir.
I said, so dipoles really matter. So remember, sometimes the dipoles are not. I mean, you can have other molecules like you've got AlCl3 that's fan shaped, and again, Cl is more electronegative. But it's like a fan, and all the Cls are pointing in opposite directions, right? So again, Cl would be trying to pull electrons, but the electrons will remain equally distributed. They're going to get cancelled out. You can imagine a bunch of electrons over here, and one is trying to pull in that direction, one of them is trying to pull in this direction, one is trying to pull in this direction. So where would the electrons end up? They're not going to go anywhere. So is this clear?
Yes, sir.
I said, what's the next one? The next one is an extreme version of a dipole. So what does the strength of dipole depend? It's dependent on. It depends on the electronegativity difference. For example, if you have more electronegative elements or less electronegative elements, the strength of dipole would decrease. Like if you've got HCl and you've got HI. Now I is slightly less electronegative, so the strength of the dipole would decrease. Is this point clear?
Yes, sir.
So what's the third one? Sorry, the second one. The second one is that's known as hydrogen bonds. So that's our hydrogen bonds. Now with hydrogen bonds, the thing is that it's an extreme form of a dipole. So when is it formed? When O, F, or N, the most electronegative elements are directly bonded to H. So in any molecule, if they're directly bonded to H, and lone pairs should be present. So I'll explain both things. So the thing is, I've got H bonded to F. Now, according to this table over here, F is one of the most electronegative elements out there. Like it's right over here in the corner. It's shaded. It's got the strongest red color. So it's very electronegative. So F would pull the electrons towards itself, and F is going to have a very strong partial negative and partial positive charge. Is this point clear?
Yes, sir. It's clear.
And the other thing is that another reason why F is going to have a very strong negative charge is because it's got these six electrons, these lone pairs. So there's a lot of negative charge over here as well. So it's the same concept except that the dipole is very strong. That's known as a hydrogen bond. So there's going to be another F with its lone pairs, and they would be attracting each other. But the force of attraction would be very strong. So that is hydrogen bonds. So whenever you see in a molecule, you see OH, N with H, or F with H. Then there's the bright chances that there is hydrogen bonding going on. So for example, you've got this positive, this one is partial negative, this is partial positive, and this is partial. So very, very strong force of attraction between the two. Is this clear?
Yes, sir.
So just remember that if you have OF or N, the one of the most electronegative elements bonded directly to H, then there's going to be a dipole created, and that dipole would be very, very strong. So that would result in a very strong hydrogen bond. Now, number three is van der Waals forces, or it has many different names. It's called London dispersion forces, and it's also called temporary dipole induced dipole, or TDID for short. Now, what happens in van der Waals forces? I mean, they always exist in all the molecules, even the ones that we studied above. They would still be present. But they're more dominant when there is no other force of attraction present. For example, when you don't have a dipole, for example, a Cl2 molecule that's perfectly covalent because both Cls would pull the electrons with equal force, right? One of them is trying to pull over here, one of them is trying to pull over here. So the electrons remain exactly in the middle. Is this clear?
Yes, sir.
Now the thing with this is that if you have a Cl2 molecule, right? Uh, Now if you have a Cl2 molecule, the thing second. Now the thing with this is that the electrons, even though they should remain right in the middle, but because of the frequent collisions, the molecules are always moving around. So the electrons get knocked to one side, then they get knocked to the other side. If they get knocked to one side, this side would become partial negative, the other side would become partial positive, right? Vice versa, the electrons might get knocked to this side, and this side would become partial negative, this side would become partial positive. So is this idea clear? That what are forming are temporary dipoles. Is this clear?
Yes, sir.
And these temporary dipoles would induce other dipoles. For example, you have a neighboring Cl2 molecule. Now, because this side became partial negative, the electrons over here are going to get repelled because of the negative charge over here. So this side would become automatically become partial positive. This side would become partial negative. So that's known as your induced dipole. So I'm just going to repeat that. Due to random collisions, a dipole is created on one of the atoms or molecule just due to random collisions. So it could be this side being partial negative or the other side becoming partial positive. So the dipoles are just, I mean, they're randomly just fluctuating around because they're temporary. They just happen for a minor instant. But when they happen, the negative charge over here would push these electrons to the other side, and this would become partial negative. This one would become partial positive, and that would result in a force of attraction between the molecules. So is this clear?
Yes, sir.
So you got three forces, right? One is a permanent dipole. That's when you have a difference in electronegativity, as long as the dipoles don't cancel each other out, depending on the shape of the molecule. Then you have hydrogen bonds, which are an extreme form of a dipole, and the third one is van der Waals forces. So we're just going to go through some of the questions. For example, over here you've got intermolecular forces questions. So, I mean, for example, over here, he's saying that NH3 has a higher boiling point than pH3. Why is that? So, what did I just tell you about? What did I just tell you about hydrogen bonds? When are they formed? When either oxygen, fluorine, or nitrogen are directly bonded to H. So that means,
Sir,
yeah.
Why is it only for oxygen, fluorine, and nitrogen?
because they are the most electronegative elements in the periodic table. Like, where's the periodic table? So, oxygen, nitrogen, and fluorine, these three at the top. So, they are one of the most electronegative elements, right? So, which is why they are able to form dipoles very, very strongly because they are able to pull these electrons close to them, like really close to them. Is this idea clear?
Yes, sir.
So, which is why I mean, so they are an extreme form of the same idea of a dipole, but they're just an extreme version of a dipole. Plus, they also have these very negative lone pairs on them, so that kind of increases the negative charge even further. So, is this clear?
Yes, sir.
Achha, this one, you've got NH3. Saying why does it have higher boiling point? Because it's capable of forming hydrogen bonds. Like it's going to be really polar. It's going to be the N has a lone pair, and N would be pulling the electrons. So there's going to be a very strong partial negative charge on N, and the H's would have a very strong partial positive charge. So the molecules would be attracting each other. So it's going to be B. Ammonia molecules have significant hydrogen bonding. So now this one. So one thing that we did not do was is saying about atoms of chlorine, bromine, and iodine. The third one. Just hold on 1 second. I said, okay, France. This one. I said one thing about van der Waals forces. Remember, I told you that van der Waals forces were that the electrons are just randomly sometimes pushed to this side, sometimes pushed to this side, right? Is that clear?
Yes, sir.
Because molecules are just randomly flying around and they're getting knocked to one side and the other side. So if you have more electrons, there's going to be more van der Waals forces. But one example is like you've got an iodine molecule, right? Completely non-polar. Polar. In total, this iodine has 53 electrons. This other one also has 53 electrons. So that's a lot of electrons. That's 106 electrons. So imagine electrons getting pushed to one side in a collision or getting pushed to the other side. So the negative charge that's going to be created or the positive charge that would be created, that would be very, very strong. So the temporary dipoles that would be created, they would be significantly stronger. So remember van der Waals forces. You've got if you have more electrons and you're going to get more van der Waals forces. So remember, bigger molecules will always have more van der Waals forces. Right? Is this clear?
Yes, sir.
So over here, he's saying that I mean the molecules chlorine and there's bromine and you've got iodine, right? So they're all non-polar, so it's all fluctuating dipoles, temporary dipole, induced dipoles, electrons getting knocked. So down the group, you've got bigger molecules, so there's going to be more van der Waals forces. So it's going to be A, that the temporary dipole induced dipole forces between molecules they become stronger. Is this clear?
Yes, sir.
So now you've got forget this one. It's saying which pair has a lower boiling point than the first substance. Uh, One other thing that I should add over here is that also remember that the C and H bond is non-polar, which means that they have almost the same electronegativity. What that means is that when you see a CH bond, the electrons are evenly distributed. They're not going anywhere. So again, it's going to be just fluctuating temporary dipole. Electrons getting knocked to one side, then maybe getting knocked to this side, getting knocked to this side. Sometimes this side is negative, this side is positive. Sometimes the other thing happens. So a CH, CNH are non-polar, and they would have partial positive, partial negative charges on them. So this is van der Waals forces, right? Is this clear?
Yes, sir. Yes, sir.
This one is completely non-polar. As- Meanwhile, if you attach the second one, if you attach a Cl over here, now all of a sudden the molecule is polar because all the electrons are getting pulled to one side. So this side would be negative, this other side would be positive. Is this idea clear?
Yes, sir.
So the permanent dipole is going to be stronger. And similarly in the second one, you've got OH over here. Remember I told you that when you have OH, that's hydrogen bonding. Hydrogen bonding is really strong. Is this clear as well?
Yes, sir.
I said now neon and argon are atoms, so they're not bonded to anything, so they'll just have van der Waals forces. Remember, van der Waals forces would always be present. The electrons would be just randomly sometimes moving to the right, sometimes moving to the left. So bigger atom is going to have more van der Waals forces. This one also has van der Waals forces, but this one, when NH are bonded, that's hydrogen bonding. Is this clear?
Yes, sir.
So just remember, when you have van der Waals forces, I mean, all of them have van der Waals forces. This one has, in addition to van der Waals forces, it also has a permanent dipole. This one has OH, so that's hydrogen bonding, that's very strong. This one is bigger in size, so that's van der Waals forces. This one is N with H, so that's highly polar and it has strong hydrogen bonds. So let me just find out if I have a playlist on this. Just hold on a second. This. Okay, France. Hello, France. Can you hear me?
Yes, sir.
I said try and send me the questions now for the ones that you can't do.
Yes, sir.
Okay, we can then continue in the evening probably. I'll find some time and see. What time is it right now in Namibia?
It's 1 o'clock, 1:21.
It's 1:21. Okay, so you have a lot of time now. We can. Where's Namibia, by the way?
It's right above South Africa,
About
next to Botswana.
as I said, you're south of. It's okay. It's south. You're in the southern hemisphere, right?
Yes, sir.
Okay, sure. So go through the questions, mark those questions, send me the questions, and we can go through over those questions in the evening. Okay.
Okay, sir. Sir, can you also please send me the document with the questions that we just did currently?
Okay, sure. I'll just post it.
Yes, sir. Thank you, sir.
Okay, take care.
Bye.